Hey folks, so in our last video we talked about where functions are increasing and decreasing and how the first derivative helps us with that. Today we're going to learn how the second derivative helps us with something called concavity. And the word concave, concave up, concave down, they've been discussed just a little bit probably in your math classes, but today we're really going to get a good understanding of what it means for a function to be concave up or concave down. So definition of concavity here. Let f be differentiable on an open interval, I. The graph of f is concave upward on the interval I if f prime is increasing on that interval. Okay? And it's concave downward on I if f prime is decreasing on that interval. Okay? So really there's four different things that we can have happen. Line tool is what I wanted there. Now, this is not a graph that I'm trying to draw. It's four different graphs. So what I want you to notice here, the top two graphs are what we call concave up. Okay? They are cupped upward, where these two are concave down. Now, this first one, the function is increasing, right? F prime of x is positive because the function is increasing and it's concave up. In this one, it's decreasing. F prime of x is negative, but it's still concave up. So a function could be increasing or decreasing and still be concave up. Same with concave down. In this one, f prime of x is negative. It's concave down. And here, f prime of x is positive. It's increasing and concave down. So we see the four different options that we have. But let's get back to this definition of concavity. Okay? It says that if f prime is increasing, okay, then it's concave upward, right? So it's concave upward if f prime is increasing. So look at our two concave ups. That would be the top. And you know what? Maybe I should just make this into even a more of a table here. Right? Okay. So top row here, concave up. Bottom row, concave down. The left is, yeah, there we go. All right, so don't mind me. So here we go. Back to the definition. If f prime is increasing, then it's concave up. So look at the concave up. Notice f prime is positive. I said that because it's an increasing function. But notice how the slope is positive and gets more positive. That means that f prime is positive but increasing. Okay? It's positive but increasing. Its slope is positive and gets more and more positive. Okay? F prime is increasing. Now in this one, it's concave up as well. The slope starts out negative. Okay, see how my pen's kind of going up and down here. The slope is negative and then gets less and less negative. So we start at a negative number and get less negative. That's increasing as well. Okay, so in both of these cases, the derivative f prime is increasing. The slope is increasing. Here it's positive and gets more positive. Here it's negative and gets less negative. Concave down, we see that the slope here is negative but gets more negative. Okay, f prime is decreasing. The slope is negative and gets more negative. Here the slope is positive and gets less and less positive. That means that f prime is decreasing. Okay, so what's interesting here is we need to figure out concavity by determining where f prime is increasing or where f prime is decreasing. And think about our last video. How do we determine where a function is increasing or decreasing? By using its derivative. Okay? So we can tell where f prime is increasing or decreasing by using f prime's derivative, which is the second derivative. All right? Now, where the derivative is positive, it's increasing. Where the derivative is negative, it's decreasing. So where f double prime is positive, f prime is increasing, it's concave up. Where f double prime is negative, f prime is decreasing, and it's concave down. All right? So how do we test for concavity? If f double prime is positive, then it's concave up. Again, f double prime positive means f prime is increasing, which means it's concave up. If f double prime is negative, f prime is decreasing, so it's concave downward. Okay? That's how we check for concavity. Okay? Now, where concavity changes is called a point of inflection. Okay? So let me just draw something where the concavity changes. Notice here it's concave down, here it's concave up. The place where it changes, and I'm going to say that's right about there in my rough sketch, where it changes from concave down to concave up, is called a point of inflection. And a point of inflection happens where the second derivative equals 0, right? So we have critical numbers where the first derivative is equal to 0, where the second derivative is equal to 0 is a point of inflection, okay? Remember that critical numbers help us tell where a function goes from increasing to decreasing or decreasing to increasing. Okay? Well, we're finding the critical numbers of f prime. Okay? So we're finding the second derivative is equal to 0. Okay? So at a point x equals c is a point of inflection, then either the second derivative equals 0 or the second derivative does not exist. Right? So we're finding the critical numbers of f prime. So that would be f double prime. So how do we find concavity? You find the inflection points, and then we test the value in each interval. So just like we tested for where a function's increasing and decreasing, to find where it's concave up and concave down, we find inflection points, and then we test the values. So find the inflection points and discuss the concavity of this graph. Okay? Well, do recall that we have to make sure that we put any values that are not in the domain, because it can change, you know, from concave up to concave down, like at a vertical asymptote or a hole or something like that. But when we take a look at this function, our domain is all real numbers, so we don't have to worry about that. So let's find our inflection points. Let's take our first derivative. Then let's take our second derivative. Where the second derivative equals 0 is our points of inflection. They're the critical numbers of the first derivative. So I'm going to solve this. Let's add 16. Let's divide by 24. What is that, 2/3? We'll take the square root. So we get x equals plus or minus, let's see here, that'd be the square root of 2 over the square root of 3. Multiplied by root 3 over root 3 is square root of 6 over 3. Oops. Okay, so those are our points of inflection, okay, or inflection points. So now what I'm going to do, I am going to set up my x-axis like my number line. We're going to put on x equals negative square root of 6 over 3, x equals positive square root of 6 over 3, and we will test a value in each interval into the second derivative. All right, so pick a value to the left of negative square root of 6 over 3. Now the square root of 6 over 3, just to make sure that I know approximately what that is, it's about 0.81. So f double prime of negative 1 would be just fine. Let's put negative 1 into the second derivative. That's 24 times negative 1 squared minus 16. That is positive. That tells me that on this interval it is concave up. Let's pick a value between these two. 0 would be the easiest. Put 0 into the second derivative. It's concave down. Okay, it's negative. It is concave down. Let's put a value in above root 6 over 3, like positive 1. And that second derivative is positive, which tells us it is concave up. Okay. So, discuss the concavity. I'm going to say concave up on negative infinity to negative root 6 over 3, union root 6 over 3 to infinity. It is concave down on negative 6 root 3 to 6 root 3. There we go. Okay, let's check it. I just want to see what this looks like. 2x to the fourth minus 8x squared plus 8. Let's just double check that. Looks good. All right, here's the graph. Okay, and does it match? Well, what did we say our points of inflection were? Negative square root of 6 over 3. Actually, let me just put it in as a point. Negative square root of 6 over 3, comma, f of negative 6 over the square root of 3, right there. And we can see that's where the concavity changes. Notice it's concave up. Right through there, then switches to concave down, and then at the positive side, oh, lost my divided by there. Okay, there's our other point of inflection. So concave up, concave down, concave up, beautiful. Okay. So let's try to on this one. Okay, our function now is x squared plus 1 over x squared minus 1. Okay. So first off, when it comes to domain, we're all real numbers except plus or minus 1. Okay, those would be vertical asymptotes. So it's important that we consider that because concavity can change. So I'm going to put negative 1 and 1 on there. All right, now let's find the inflection points. So first derivative. Bottom, d top minus top, d bottom over bottom squared. 2x cubed minus 2x minus 2x cubed minus 2x. That's just negative 4x, isn't it? Over x squared minus 1 squared. There's our first derivative. Second derivative time. Quotient rule again. Bottom d top minus top d bottom, chain rule, 2x squared minus 1 to the first times the derivative of the inside, 2x over bottom squared, which would now be the fourth. I'm going to keep working on the next page here. Well, I do notice this, that there is an x squared minus 1 in every term. So this one of those, and one of those will cancel out. Make that to a third. This one to a first. So now I'm going to distribute negative 4x squared plus 4. Back here I have 4x times 2 times 2x. So that's 16x squared. So I have 12x squared plus 4 over x squared minus 1 equals 3. That's my second derivative. Now I want to find where that's equal to 0. And I know what fractions equal to 0 only where its numerator is equal to 0. And it doesn't take me very long here to recognize that I'm going to take the square root of a negative, which is imaginary. So that tells us there are no points of inflection. Okay? There is no point where the concavity changes. Okay? Now, no point that exists. Recall, though, that at vertical asymptotes, okay, the concavity can switch. However, it's not a point of inflection because there's no point there. It's not defined. So we're just working off this, and we're going to test the value in each interval. I'm going to suggest negative 2, 0, and 2. All right, let's start by putting negative 2 into our second derivative. Okay. Now, negative 2 is going to give us a positive in the numerator and a positive in the denominator. And a positive divided by a positive is positive. Whoops, wrong direction. So the second derivative is positive in this interval, which tells us it's concave up. Now at 0, looking at my second derivative, I get a positive. This would be a negative, right? Negative 1 cubed is negative 1. So a positive divided by a negative is negative, which tells me here it's concave down. And at positive 2, we have a positive over a positive, which is positive. It is concave up. So our interval is concave up, negative infinity to negative 1, union 1 to infinity, concave down on negative 1 to 1. There's our intervals of concavity and no points of inflection. Now, recall that we've been working a lot on extrema. And how can concavity help us with extrema? Well, we have something that we call the second derivative test. Okay? If we have a critical number, okay, where f prime of c equals 0, where the derivative is equal to 0, then if the second derivative is positive, okay, now think about what that means. If the second derivative is positive, it's concave up. And we said at c, the first derivative is 0, so it has a slope of 0. If it's concave up at a critical number, what do we have here? We have a relative minimum. But if the second derivative is negative, it's concave down. And if it's concave down at a critical number, then it is a relative maximum. Okay? So this is a nice test to determine if a critical number is a minimum or a maximum. Is substitute it into the second derivative. Okay? So find all extrema of this function 5 plus 3x squared minus x cubed. Okay? So how do we find the extrema? First, we have to think about the domain. Okay? Domain, all real numbers, nothing to worry about there. Now we have to find the critical numbers. Where is the derivative equal to 0? So our derivative would be, that's 0, that's 6x minus 3x squared. Let's set that equal to 0. I'm going to factor out a 3x. That's 2 minus x, right? Looks good. X equals 0 and x equals 2 are our critical numbers. Okay. Now I could, okay, think about our last video. I could use our first derivative test, draw my number line, determine where is the function increasing, decreasing, and see where does it change from increasing to decreasing or decreasing to increasing. But I want to use my second derivative test that I just learned about. Okay, so I'm going to take the second derivative. So here's my first derivative. My second derivative is 6 minus 6x. And my second derivative gives me concavity. So I'm wondering, at x equals 0, is it concave up or concave down? Well, f double prime of 0 is what? Positive. That tells me it's concave up. And if it's concave up, x equals 0 is a relative concave up minimum. How about our other critical number? F double prime of 2. Substitute 2 in here. 6 minus 6 times 2 is negative, which tells me it's concave down. And if it's concave down, it must be a maximum. Okay. So look how easy that second derivative test is on this problem. Okay. We work through the first derivative, get our critical numbers. We take our second derivative, we substitute our critical numbers in to determine if it's concave up or concave down. Okay. Now, I do want to say this here. Is the second derivative test always the better? Is it always better than the first derivative test? And the answer is no. Okay, when I want to determine if a critical number is a minimum or maximum, I look at the individual problem and decide, do I want to use the first derivative test or do I want to use the second derivative test? If taking the second derivative looks like it's going to be nasty, I'm not going to do it. I'm just going to use my first derivative and determine where is the function increasing or decreasing. But on a problem like this, where the second derivative is a piece of cake, I'm going to go that route and determine if it's concave up or concave down at the critical numbers to determine the extrema. All right, so awesome option. Okay, really nice to tell where the function is concave up and concave down, along with using the second derivative test to determine extrema. Now, our goal here is to get to the point where we're drawing the best graphs of our life. And I hope you're starting to see we're putting a lot of the pieces together on any function. Okay? We know where the function's increasing, decreasing. Now we know where it's concave up, concave down. From pre-calculus, we already know about vertical asymptotes, slant asymptotes, horizontal asymptotes, holes, okay, domain, range, end behavior. Man, put extremas on there, you can tell that we're really putting it together. So it looks like that was my last example, so I'm going to wrap up my video. Thanks for watching. We'll see you later.